Okay, let's get started. Today we're going to talk about how to design heap allocator. Basically, our heap space is a linear space in a virtual address space. But applications do not even consider this linear space. They consider it just a simple type of object in Unity called memory objects. We like to explore their design decisions associated with it. And in order to understand modern implementation of heap allocator, we're gonna implement everything from scratch by ourselves. Okay, and then next week we're gonna talk about the security issues associated with it and how to exploit them. There's some administrative in-class CTF is scheduled in December 1st. Please submit your team's challenges as soon as possible. And whenever you need some ideas, feel free to talk to TA or myself. We can brainstorm about the new trends in security issues last year and this year. And we highly recommend to minimize those security issues in small challenges so that other people can get some lessons by solving those challenges as well. We also highly recommend start solving NSA code-breaking challenges as well. So we like to give extra bonus if you really complete near the end of NSA code-breaking challenge. We're gonna give extra bonus. Last week, you guys explored a little bit different kinds of security issues, such as integer overflow, from the race conditions, and sandboxing bypassing, and many of those small little details in security issues. Some of them are beyond memory safety issue we've been discussing so far. But these are the trends of security vulnerabilities which are reported by Microsoft. If you see this top of the graph, it represents the amount of vulnerability in stack corruption. In fact, it's pretty consistent, right? But there's an interesting type called heap corruptions and UGF free. If you see the bottom two, a little bit lighter blue and here. In fact, the major part of those vulnerability are heap overflow, and some more vulnerability related to the heap. These are the topic that we're going to talk about today. Why heap vulnerability are critical? There are many reasons behind this. Similar to the stack overflow, heap object can overflow as well or underflow, depending on the situations. And because of the nature of the heap, in fact, their lifetime is much longer. And typically, the complex logic require the heap allocations. Otherwise, you just allocated something in the stack, and their lifetime is very short. So that it's hard to make such mistakes in the local context. On the other hand, the heap objects typically have much longer lifetime. That's why we allocate heap at the first place, similar to the global variable. Not only that, many of the heap exploitation techniques do not require application context. It means if you have a way to overflow them, instead of leveraging some of the context of the applications, you can also exploit heap implementations as well. In fact, as you will see today, heap metadata and their corresponding infrastructure behind are very vulnerable to those type of overflow, and which we're going to explore today and next week as well. Okay. In other words, if you ended up finding heap-related vulnerability, although it's very complicated, then there is a universal way to exploit them. Given a simple overflow, you can make them a arbitrary read and write, or even executable at the end. We're going to explore all these design decisions behind heap allocations and their security implication. Not only that, in next week, we're going to explore exploitation techniques, right? Instead of presenting their design, the modern heap allocator is extremely complicated. If you consider ptmalloc, which is the latest implementation that most of the Linux systems rely on, they consist of 40,000 lines of code, right? It's not a simple piece of software. It's very complicated, but their main design goals are pretty easy to understand. and you can actually build a heap allocator by yourself. Although the modern implementation of heap allocation is very complicated, but we can in fact design them with the very simple interfaces that they provide, right? So can I write? Okay, there are two interfaces the heap allocator provide. What are those? You guys remember? How to allocate the memory? Exactly, we invoke malloc. So in the malloc, what are the argument? The size of the object that you want to allocate. What does it return? Exactly, it returns pointer to the allocated memory region, right? What if we fail? Return 0 or null pointer, and then it indicate the condition of the error number, which you can access as a global variable in your C program. Once you're done with this object, how do you do? What do you do? Free the objects, right? What's the argument of the free? Pointer that you want to free. What is your return value?
I think it's like 1 or 0.
No, free doesn't have any return. In fact, its return prototype is void. It doesn't mean, it means there is no error condition that invocation of free fail. So whenever you invoke free, it always succeeds, unlike malloc, right? What are the condition malloc couldn't return pointer? When malloc fail? If your system doesn't have enough memory, it fails. Right? Often it fails all the time. Right? It's out of memory conditions. Right? Although the interface is pretty simple, but there are many corner cases you can think. For example, what about we invoke malloc with the size of 0? What does it return? What do you even mean by allocating with the object size 0? Any guess? What does it return? What? Null pointer is a pretty reasonable guess, right? But in fact, it actually returns a valid pointer. What's the reason behind those? Any guess? There are long discussion in the Linux community whether it's a right to return null versus is it right to return the valid pointer. But the other team win over time because of certain patterns in the application. Can you think of why? Once you have this pointer, you sometimes want to reallocate it with a different size. If you have certain pattern of allocation, you get the size whenever you need, you reallocate. So it's reasonable to have a valid pointer so that even if object is 0, you don't have to treat those allocations specially with the free, right? So it return a valid pointer, so you can either free, you can reallocate, you can do whatever you want, but you cannot override. There's a very interesting pointer that you can get out of this return. What about we invoke malloc with -1? What does it even mean? It means what's the type of this size? What's the type? it's a size t, right? And what does it mean by providing -1? What? Int max? Or
The size and size.
what? This -1 will be converted to the size which is unsigned integer, which is max value of unsigned int, right? Did you return? It basically, you request allocations about 4 gigabytes. Does it? What's the size of your laptop? 32 gigabyte or 64 gigabyte these days? You should allocate something, right? In 64 architecture, you try to allocate. In 32-bit architectures, say you're running 32-bit applications in 64, you have enough memory, but this guy actually failed because of some of the conditions that the GNU malloc require. In fact, you can only allocate it to the max int, not the unsigned max int. So it likely just return null, right? And what about after we allocate something to the some size, to some reasonable size? What if we access this pointer? What are you going to read? What does it return? Basically, we allocate the new memory by invoking malloc. We access something inside. Yes?
I think it depends on the type of the pointer. It will reference one of those values.
Yeah, it might read something, but what are those values? Exactly. We don't know, but you will see some of the pattern that you're gonna see here. Once you allocated something, there is a two possibility. Particularly in these cases, you're gonna read the very first memory inside the object, which typically have a pointer to another heap objects. In fact, you're gonna have a data pointer. By reading those, you can in fact decipher entire memory layout of the heap space, or sometimes you're gonna read some of the previous value that other memory was just free, right? Depending on the such conditions. What about after we disallocations? What about we access more than the size? Maybe size slightly over or under. What's gonna happen? In fact, you just did out of bound read, out of bound write, either overflow and underflow. These are undefined behavior in C, meaning that compiler can do whatever they want. But when it comes to actually compile binary, it in fact reads something which is out of your allocation, right? But the return value of this pointer is not guaranteed depending on the application. Context likely reads some of the object allocated next to you, right? This is we typically call overflow or out of bound read, out of bound write. Say overflow, right? Okay, let's talk about free. What about we do free on null pointer? Just provide 0. Doesn't have any return value. What's gonna happen? What do you mean by freeing null pointer? Does it try to deallocating the very first virtual address starting with 0? In fact, application can get the first page starting with the 0. your virtual address is starting from 0 to 2 to the 32 in 32-bit architecture. This is complete free space. But for security reasons, most of the application is not, operating system doesn't provide this first couple page so that they can detect the null point dereference, for instance. Otherwise, null pointer, in fact, returns something. This is legitimately allocated. Like if you consider 10 years ago, this typical exploitation technique against the kernel. But nowadays, it's not very common. So one of the security measures in Ubuntu, for instance. What's going to happen here? Sec4 is very reasonable, but in fact it's actually no, meaning that you can invoke free with null pointer all the time. In fact, this is a pretty convenient in terms of C programming, meaning that what if your allocation fail, and then you can probably you're gonna jump to the error condition routines with the goto, for instance. They likely have this free. Otherwise, you have to check whether pointer is null or pointer is valid and invoke the free. Right? This is one of the convention that you can just pass any pointer to free, so you can free. Right? If it happened to not contain null, just ignore. It's a pretty nice implementations in the free. But what about we provide free with some arbitrary pointer? What's gonna happen? What about we provide a stack pointer to free? Any guess? Basically, some of the pointer that you didn't allocate through the malloc, but you provide to free. Any guess? Likely sec fault. But you're gonna see some of the interesting exploit technique associated with this. In fact, you can free some of the objects either in stack or arbitrary heap regions if you have proper metadata. If you have arbitrary control contents of the heap or stack, in fact, it's easy to create the valid pointer that can be free. As far as you can create the metadata nearby, then in fact you can free the object so that you can leverage this one as attack vector. So as far as the attacker can control this pointer, it's a serious exploitation technique. Okay? What about we do free? And then free one more time. After this free, what is the value inside? So after this free, this pointer going to be null. In fact, you just pass the pointer so they cannot modify. So pointer will just stay the same. So it is not null. But what if we access the pointer? It would be great if sec fault, but in fact it contains something similar to the malloc conditions. Likely it contains some of the data pointer you can leverage as well. You will see such a pattern today. What about this one? So pointer doesn't contain null. If pointer contain null, this is nicely noted. Unfortunately, pointer is already free, and then you try to free one more time. What's gonna happen? Yes?
If the metadata is there from maybe some other, if it was reallocated something, it's all the metadata, but we'll still try to free it again.
We try to free again. In some cases, in some of the implementation of heap allocator, they consider free this object 2 times. In fact, you allocate it after this, then it will return the same pointer 2 times. In fact, because of this, in fact, you can easily create a race between this. This is one of the serious vulnerability, what we call double free. Right, as name said, free 2 times. So say DF. This is one of the technique that whenever you see double free, easy to exploit. It's one of the very serious vulnerability. So we're gonna explore other conditions. In particularly, in this case, we free these memory regions and access. So this type of vulnerability is also very easy to exploit. And one of the common vulnerability that I show you today is called use after free. As this name indicate, we're gonna use after free. So we free and then we use this pointer. The security implication of this is very subtle. If this pointer is no one is using this pointer, likely it's just fine. But there is many chances that between these 2 free and use, another thread might allocate a new object, which means your pointer pointing to some of the legitimate memory region that other thread is using. If it contain a, I would say, function pointer, in fact, you can override those function pointer with this use after free vulnerability. In fact, this is one of the dominant type of bug in modern complex software like browsers and kernel. In this class, we're gonna explore these 3 conditions of heap exploitations: overflow, double free, and use after free. We have 3 design goals when we are implementing heap allocator. One is performance. Performance is arguably the most important aspect of heap allocator. Otherwise, we don't need the heap allocations at all. We're gonna see one of such design today. Why we have heap allocator? We like to reuse the memory, so that the main purpose of heap allocations in your systems is provide a way to reuse entire heap space, or you utilize the heap's memory as efficiently as possible. Equal utilization, or in other words, fragmentation. If memory is fragmented, we cannot properly utilize the entire memory space in the heap. There are 2 types of fragmentations. The internal fragmentation, which is pretty simple. You allocate some, say, a page. In fact, although entire system is allocated this amount, the smaller amount is only usable, so that we have some fragmented memory regions internally in this allocated region. So we call internal fragmentation. Another type is external fragmentation. This is more subtle. You have, say, a sequence of allocations, like assuming there are 3 allocations happening in the systems, and there are some free memory regions. Say these are the freed, and if a system requests some of the memory which is bigger than these 2, each of these 2, so that we cannot put this one to here or here. But if you combine these 2 free memory regions, it's bigger than this guy, which means it's externally fragmented, so we cannot utilize the entire memory regions because of these properties. All the heap allocator try to reduce these 2 types of fragmentations, internal and externals, by design. Lastly, people consider security. There are lots of security checks associated with the heap allocations, or sometimes you can design heap allocator can prevent all these three heap allocation related security vulnerability. The best way is to remove the heap allocations completely so that you don't have security implications associated with heap. Unfortunately, that's not realistic. You need those memory utilization and performance in your application so that security issue naturally come when it comes to design of heap allocation. Let's first design very simple heap allocation, say version 0. It's a simplest type of heap allocations, but surprisingly most secure way. It basically means we can prevent all three of security issues by design. Right? Here, in this interface, we're gonna do simple mapping to the system calls. It means if you have malloc call from the application, we simply redirect to mmap. What does mmap do? What's the purpose of mmap? It allocates the page, not the memory region. Means if you request, say, size 10, it allocates one page. What's the typical size of the page? Yeah, 4 kilobytes. If you request 10 bytes, it ends up allocating entire page for you. It's okay. You got the memory that you can write 10 bytes. What about free? What about we have pointer with the free? We simply redirect to m onmap. Alright? It basically means that whenever you got the pointer, we reclaim the entire page. It seems like very good in terms of security. Why is that? Assuming that you allocate this memory region, say you have the pointer here. In fact, you can override 10 bytes. What happens if you override beyond 10 bytes? In fact, no one is using these memory regions. You're the only one. What if we go beyond the one page? No, it's gonna set fault. Basically, it provides very nice boundary between the objects. So whenever you have this interface, we are not suffering from usually have the free even. Why is that? Whenever you free the entire memory region, it's unmapped. But if we access the unmapped memory region, it's gonna set fault. In fact, in terms of security, all these security concerns are simply gone. We cannot do override, overflow, or underflow. We cannot do double free, which when you are trying to free the free memory region, you're gonna set fault. If you try to go beyond the allocated memory region, you're gonna set fault, right? If you try to do usually after free, you're gonna access the free memory region, which also set fault. In terms of security, this is the best possible design. But why we are not using this? It's very inefficient. In terms of performance, it's really terrible. Why is it terrible? Whole purpose of the heap allocator is to avoid the invocation of the system call. System call is very slow operations. Typically in modern architecture, it takes about 2,000 and 5,000 cycles. And memory related one requires a lot of operations. You have to modify page table, and you have to flush TLB, which is typically very slow in modern architecture, particularly many core systems. So again, whole purpose of having heap allocator is to avoid the use of extra system calls, right? If you ended up having extra system calls is not usable as a heap allocator. What about the fragmentation? It's really bad in internal fragmentations. We ended up allocating way more than necessary. If you're having smaller object allocated, you ended up having way bigger allocation segment per page size. What about external fragmentation?
It would be pretty low because if everything's like the size of the page, then eventually it will
Yes?
Not necessary that having this page is on.
Exactly. Here, whenever you return, in fact, this memory, the page will be reclaimed by the operating systems. So when you request a bigger size, you can always reuse this reclaimed page by the operating system. So in fact, there is no external fragmentation associated with this scheme because the free memory will be always reclaimed as a page. And whenever necessary, they're going to concatenate this large page and make a contiguous memory regions, which is exposed as a virtual address space, right? This is interestingly fragmentations, we are only suffering from internal fragmentations, not external one. So in fact, this is a pretty good, right? Or not terribly bad as we imagine. But again, the reason that we are not using this memory allocation, because the performance is most important aspect of the heap allocation. So let's redesign another one. This time, we're gonna design very much focus on performance. Fastest possible heap allocator. Okay. The basic idea is that we're gonna keep track of a global pointer pointing to the end of the heap space, say global pointer. Okay. The basic idea here is that given this large memory space, we're gonna keep maintaining this global pointer pointing to the unused heap space, right? Typically top of the heap space. If malloc happened, say we allocated some of the memory and stored to the pointer 1, we request the allocation of size 1 and we got the pointer. What it does is very simple. It simply returns the global pointer, say this is now pointer 1, and increment this global pointer by size 1. Meaning that now the global pointer pointing this memory space, because these are the free spaces so far. For the allocation, we simply did one arithmetic. Just increment the addition of the size 1 to pointer, global pointer, and return the pointer. So this entire memory space is now usable, right? What about we do another allocation, pointer 2, and malloc with size 2. Again, similar to what we did, increment the global pointer by size 2. And we're gonna return this pointer. This is pretty usable space, right? But what about we do free? Say we try to free the pointer 2, which is this allocated memory region. Any idea? Yes?
Move the global pointer back to like by the size.
Yes, that's a pretty good optimization. If we ended up having the previous memory region is free, in fact, you can check the global pointer pointing to the last object. We're gonna reclaim this one back by subtracting it. But what about we free this memory region, the first one?
How will you know the size?
What do you say?
So free doesn't have a size. How will you know how many?
That's a great question. So we're gonna try resolve this issue later. But when it comes to free 2, we still have to check whether pointer 2 is really the last object. Without having size 2 recorded somewhere, it's hard to even check. In fact, we're going to explore many different tricks to restore this size 2 in the heap allocation design. In other words, we don't even know pointer 2 is actually free or not, or next to the global pointer, without having this size 2. So, in this version 1 scheme, we're going to ignore this entire free and map it to no. See, in other words, free is extremely fast. It's nothing. We just ignore. What about we have another pointer allocation? So we ignore this free and keep going. Right? We're gonna increment the global pointer by size 3. And we're gonna return this memory region as a pointer 3. It's pretty good, right? Let's just think about some of the security issues and design goals that we discussed. Let's go down. In terms of performance, it's extremely fast. Even free is no. Malware is just one arithmetic. It's just super fast. Probably you cannot implement anything better than this one in terms of performance. What about fragmentation? Do you have an internal fragmentation? In fact, we're gonna allocate perfectly sized all the time. That's amazing, right? There's no even unused space in the memory space. So internal fragmentation is amazing, but what about external fragmentation? So in this case, this memory region is not even used, right? You're always gonna suffer from external fragmentations if applications ended up invoking many free and alloc in their lifetimes, right? Seriously bad in terms of external fragmentation. You can imagine that if you have this type of allocations, your system easily ran out of memory, right? Because there's no reuse of the memory in this scheme. What about security? What about overflow in this case? What if it overflow happen, say, starting from this guy? In fact, you can overflow many other objects, right? So in terms of overflow, there's no protection. But what about double free? So we first free these objects and free again. What's gonna happen? Nothing happened. The free is just knob operations. In other words, in terms of double free is amazing scheme too. But what about use after free? So we free these memory regions. What if we reuse? In fact, you can reuse it as many times as you want if no one is using these memory regions. In fact, this basically eliminate the use after free vulnerability, because think about it, there's no free, so there's no use after free. So in terms of security, is amazing schemes. In fact, in terms of overflow, you're gonna see later, because it doesn't allow application to override the metadata, which is typically the sensitive region. In fact, overflow or underflow is very good too. It only overrides some of the content of the next allocated memory objects, right? So in terms of security, I'm gonna give 1+ to these allocations, right? In fact, the later modern heap allocation schemes are really bad in terms of security compared to this implementation. Again, in terms of performance, there's no way you can beat, right? But why we are not using this in modern heap allocations? Yeah, allocator.
Zero like cleanup.
Exactly, there's no reuse. In fact, Again, the whole purpose of having heap allocations is to reuse the memory, and we can have better performance by not invoking this system call, right? So we have a research project that follow these schemes that we can make the free literally null, but we can keep forwarding these allocations, but we can let the operating system that reuse these pages as much as possible. So we have very active research going on in this area as well. So let's redesign another heap allocator. Okay. At this time, let's think about how to reuse the memory. Any idea? Reusing freed memory. Any idea? Yes?
This approach is using a linked list of free memories.
Exactly. We're gonna keep track of those free pointer. Let's introduce a free list. Say it's similar to the global pointer. This free list contain a list of the pointer. It's just a list, so that whenever you free, we're gonna put to this list, right? Pointer 1, right? In similar situations, right? Say we have these 3 allocations that have pointer 1, pointer 2, pointer 3. We're gonna do exact same thing as before. So we keep track of this global pointer, right? Similar to this guy, the previous one, do. But whenever we do free, instead of making this free knob, we're gonna put this pointer 2 in here, so that we basically keep track of the free list, right? And then what about we are doing another malloc? So we're gonna do another malloc. Can you imagine the implementation of malloc here? Exactly. We first gonna check the list of the object one by one. If size is equal or less than the previous one, we're gonna just return the pointer, right? What about we do another free? Similar to what we did, we're gonna put back to the free list. In fact, you have to really think about actual implementation of this, right? In fact, you're gonna see many loopholes. Say, in this case, we got this implementation of malloc. What we're gonna do, we're gonna iterate entire pointer in the free list, and then we're gonna compare the requested size is bigger or less than or equal the size of the free objects in the free list. Then what are you gonna do? We're gonna unlink this pointer from the free list and return, right? Otherwise, what are you gonna do? We're gonna simply, we couldn't find anything in the global pointer, so we're gonna increment this size. Say store the G pointer ahead of time and increment and return pointer, right? So in this case, the new allocation happened right next to it. Otherwise, you're gonna iterate. What about free? We simply append this pointer to the free list, right? It's pretty simple. Do you guys see any loophole? Again, as someone mentioned before, how do we get this information? How to get the size of certain pointer? Yes? So we need some metadata associate this pointer. Assuming you have a key value store, you put the pointer, you always return some of the objects, a size of the objects. Assuming you can have separate metadata store, say key value store, you can get this information. In fact, whenever you do such operations, you have to keep track of them. In fact, there are two different approaches, right? Equal in-place metadata. This is a typical or it was popular method, but in fact, modern implementation try to avoid this in-place metadata. But let's focus on the implementation of BTML. They keep track of this size as part of the object, so-called in-place metadata. Or, again, similar to the key value store, you can maintain such information out of band, like key value store. What's a good way to implement this in-place metadata? Any suggestion? How to quickly look up the size associated with this?
Could you make the encryption store each point?
Exactly. As part of these allocations, we say we got the allocations of certain size. Instead of just allocating this size itself, we're gonna allocate a little bit more. Meaning that right before, say we allocated this bigger amount, right? Basically size plus 4 instance, right? Or depending on the architecture, size plus 8. Some of the word size in your architectures, and store the size right before the objects. But you allocated this bigger amount, but only return some of the pointer in here. So the application will use this smaller value, but you're completely fine. Similarly, say we're gonna store size 2 in here and size 3 here. So given a pointer, you can always check its size by subtracting this pointer minus 4 and read, right? Which are pretty nice. So we don't have any problem of getting these informations with this new in-place metadata informations, right? Let's evaluate this implementation. In terms of performance, is it good or bad? Free, which are pretty good, right? You can just append, likely just constant operations and return. What about malloc? What? It's okay. What about we have so many free objects?
Well, maybe it's good.
Exactly. If you have many free, it ended up spending ON with the number of the free objects in your systems. I'll give -2 the performance because of the malloc. What about fragmentation? Previous implementation doesn't have internal fragmentations. What about this guy? Because previously we're gonna allocate the exact amount, but in this case, what about we request the size which is smaller than the free? In fact, you're gonna have a smaller memory region that you're gonna use. We're gonna waste the previously used in the free list. So in terms of internal fragmentations, it's not good. What about external fragmentation?
It has to be external fragmentation because you're still allocating, you're returning the pointer with a new size, or is the size like the same? So when I have a smaller size and I get a pointer that has a bigger size, am I overriding the like actual size metadata of that pointer?
Oh, sorry, could you repeat the question one more
So
time?
you're saying that there's internal fragmentation, but would this not be external fragmentation? Because like if I have a size that's less than the size of the metadata, it's going to give me that pointer. Would I overwrite the size now with the smaller size, or
No, we're gonna just keep the same size so that in terms of metadata, it should be consistent, right? Whenever this pointer is pushed back to the full list, we're gonna still keep the same size, right? But it's okay to return a pointer bigger than what you requested because you're gonna just overwrite the smaller amount anyway, right? But in terms of external fragmentation, similar to the previous implementation, you're gonna still suffering from external fragmentations. You might have many free lists here and there, which is bigger than what you're requesting to the heap allocator, right? What about security? In terms of, say, overflow, exactly, you ended up overriding size even, right? In other words, if you have 1 byte override, you override the size. You mess up with the heap metadata, it might affect the implemented behavior of the heap allocator, which is really bad. What about user after free? In fact, your free pointer now reuse the free memory region that you reuse. Your free pointer now ended up overriding some of the data of the other user, which is also really bad. What about double free?
also pretty bad.
It's terrible, right? You ended up pushing 2 pointer to the free list, meaning that you ended up putting the 2 pointer to the free list, meaning that you're gonna return the 2 pointer at the same time. You ended up messing with the entire applications. So even though we start having some little bit of improvement of memory utilization, we start compromising rest of implementation. Okay, here we like to improve the performance, and we like to improve internal and external fragmentation by redesigning the heap allocator in the next version. But as you can see, because of this complexity of the heap allocator, all of these security start being compromised, right? Basically, you're gonna get additional behavior and benefit by compromising security of the heap allocator. So let's implement another heap allocator to the version 3. So handling fragmentation. Any idea? Is there any way you can improve the internal fragmentation? What do you say? Oh, that's a good suggestion. So one of the suggestion here is that iterate entire free list. Are you gonna list, and are you gonna return the perfectly sized all the time? Exactly. But do you prefer to have this one? Previously, whenever it hit one of the element in the free list, which is bigger than the requested size, you're gonna return, which is suffering from, I would say, internal fragmentations. Now you only look for perfectly matched free object. In fact, it's not a bad decision. But do you see the frequent use of those case or not? And you always pay for the worst case, basically the NON of the free list all the time in common path of malloc, unfortunately, right? I rather want to avoid this situation. In common path, I want to get constant as much as possible. It's a better way to utilize, reduce the internal fragmentations. Better idea. Exactly. That's a great idea. In fact, you don't have to return the entire free objects. You're gonna split, right? It basically means, so given somehow you find this memory region which size is bigger than the requested size, say this size 1, say this is actually in the free list, right? What we're gonna do, we request the size, we're gonna remove this one to the size, and we only allocate it, break this one, split to the size amount, and then we're gonna create another free object right next to it. What's the size of this guy? Size 1 minus size minus 4, because we now have an extra metadata, which is this is size, right? And then instead of just keeping this one removed from the free list, we can point to here, right? You basically split the free objects and now push back the unused amount back to the free list. In fact, that's a great technique. In fact, it happens all the time when you're singing the actual modern implementation of heap allocations. How to deal with the external fragmentation? Better, any idea? In this case, we split. But there are special cases that we can handle external fragmentations when the two free objects are next to each other. Like similar to condition that you mentioned in previously. Think about this way. Say you have the size 1 worth of the free pointer here, and then later you want to free this second objects. Say this one is already in the free list, and you ended up freeing these objects. Then instead of pushing this one back to free list, we're gonna merge. How would you merge? Just remove this guy and modify this size 1, 2, size 2 plus we have extra data here 4. In these cases, then you now ended up having bigger free objects so that you have more chance to reduce the external fragmentations. In fact, this is a special case that what we call forward consolidation, because you merge this object with the forward objects. For free object stay right before this object that you want to free. In fact, there's another consolidation technique called backward consolidation. It's a pretty similar situation, right? In this case, you try to free this size 1. This pointer is already in the free list, but you want to free this guy. In this case, we're gonna remove this pointer dash from the free list. We're gonna push the pointer back to the free list, but we're gonna consolidate this, modify this size 1, 2, size plus size 2 plus 4. Pretty similar. In this case, we're gonna consolidate back to the object after, allocated after, right? In these forward and backward consolidations, in fact, you have more chance to merge. So given a pointer in free now, if you think about the implementation of this free, we first gonna check whether previous object is free or not and consolidate. We're gonna check whether forward object is freed or not and consolidate, and then push back to the free list, which is pretty simple, right? But should I keep consolidate more and more recursively back? Or this operation is still constant? In fact, because you keep, whenever you got the free request, you're gonna consolidate, which means there is no object stay next to it. Meaning that you don't have to keep recursively consolidate. It's just one-time operations in free. You just try to consolidate forward and backward whenever free requests happen. So in terms of malloc, because of this technique, what we gonna do, we first gonna iterate this entire free list. Whenever you hit, we're gonna split the objects, push back this remaining one to the free list back, and return, right? It becomes a little bit complicated. But in terms of performance, is it good or bad? Free is still constant. The malloc still, we have to iterate once, but it doesn't have to iterate the entire list, just very first object that hit, right? In terms of performance, it's the same as before, because the free is still constant. But we have a drastic improvement in terms of internal and external fragmentations, right? In fact, this is one of the best design and modern implementation of the heap allocator have this behavior. Like this is the only way they can address the memory we use with the smaller amount of fragmentations internally and externally, right? What about security? If you have overflow, you still overwrite the metadata. It's the same as before. In terms of double free, it's the same. In terms of user after free, it's the same, right? But in fact, because of those, we actually improve this guy significantly, right? So I think the current problem is this performance. What's the best way to improve the performance? Any new idea? So we're gonna explore the last design. Performance optimization. Any idea to improve the performance of the current implementation of Heap allocator? The only problem here, when you're doing malloc, you have to iterate the free list. Yes?
Could you sort the free list by size?
That's a great idea. In fact, that's one of the decisions that most of the modern heap allocator using. So we are maintaining this free list in the sorted manner, right? Because we have access to the size. Not only that, because it's a sorted list, what you can do, how would you search? Yeah, in fact, if you implement it well, you can do the binary search as well. So this enables a lot of improve the performance of implementation significantly. But still, you have to do these log n operations. In fact, this actually improves the chance to hit the right size because everything is sorted by size, right? You have more chance to have a perfectly sized objects or object nearby. Any other idea? Or, in fact, there is a pitfall. Previously, we talked about this one naively, meaning that in order to check whether certain object is free or not, for example, when you're doing forward and backward consolidations, you have to check. You have a size, but how to check whether this one is free or not? You have to iterate entire free list. right? This is really bad decision. In fact, in terms of performance of this, we naively thought it's constant operations, but in fact it's not. But in fact, there's a way to make it constant. Any idea? Anyone?
You have more metadata that tells you this is free.
Exactly. You can create the metadata that indicate whether it's a free or not. Where do we put the metadata? End of the allocated space. That's one way. Any idea?
Inside the Heap inside.
Inside the free page. We're gonna talk about that later, but not. What? What? Could you? Before the allocated object? That's sort of right, but we don't want to use more than the size itself. Any good idea? In fact, previously, this is a layout of the object. We have a size. We allocated 4 bytes more than requested already. Is there any way we can squeeze this one? Are you gonna use the entire 4 bytes? In fact, not. Maybe top of the bytes is not usable. You're not gonna allocate it to the 32, as we discussed before. In fact, one bit is available, right? Without suffering anything in the here. But at the same time, there's a common requirement of the heap. You like to use the heap space in a line manner. Even if you request the 1 byte request, you're not just gonna allocate just 1 byte here. In fact, you're gonna allocate way more than a line size. In modern implementation, and we're gonna talk about later as well, we typically align the minimum size of the object the system allocated is the 2 word size. In the 32-bit architecture, they're gonna allocate it about 8 byte, which is basically 2 element at least, right? Which means, say alignment of this object size is 8 byte. How many bits available here? Yeah. In fact, there's a 3 additional state we can use in the size without suffering from without allocating any more data. In fact, this is right after this one, right? So we're gonna introduce a weather state bit that indicate whether this memory region is used or not. Say U is basically called in use bit. If this is 1, meaning that this one is allocated. If it's equal to 0, it means it's free. In fact, now we resolve the previous issues. Instead of iterating entire free list, we can quickly tell, given a pointer, you subtract by 4 with 1 bit, say is this used or not. It's pretty nice, right? We improve a little bit of performance here. But how to quickly tell whether the previous object is free or not? Say, given this one is a free object, say given this one is a pointer, how do you know the next one is free or not? In fact, you know the size of this pointer is stored before, plus the size you're pointing to the metadata of the previous one, plus 4 is the object right next to you. And then we're gonna check the use bit, right? So given a pointer, we can quickly check the next object is free or not by this simple arithmetic, right? Given this pointer, we're gonna plus size and just read and check the first one is used or not, right? So that we can do the 4 consolidations. What about backward consolidation? How can you find the previous objects right next to it? Previously, we iterate the entire free list and see if it's actually free or not, do the simple calculation. But what about this guy? How to find the previous one? Any idea? At least you need to know the size of the previous object given this pointer. Any method we can do? Yes?
Include the size of the previous in the order.
Exactly. Unfortunately, we ended up having additional metadata associated with this structure, which is very sad, right? You can say this is previous size. Say, given this pointer, fetch this previous size, go all the way to here, and then we're gonna check the status bit here. That's unfortunate. Any other trick that avoid the use of the previous size? This is an ingenious trick that people implement. We're gonna introduce another flag called previous in use. It's called P. Say previous in use. It basically indicates previous object is free or not. It means previous one is used. 0, it means it's not. Whenever P state 0 is not used, we're gonna store the previous size. What does it mean? If it's 1, this memory region will be used as part of the previous object. We're never gonna access this one. It's because it's owned by the previous objects. But if it say previous flag indicate 0, meaning that no one is actually using this memory space. In fact, we're gonna, as a heap allocator, we're gonna start utilizing the free memory region. Say that whenever it's 0, it means this previous free memory region contain previous size. So you can fetch and go all the way up. Right? Yes?
Isn't not like a security issue that like if you free the top one, it then has to modify the metadata of the
There's a serious security implications. We're going to talk about just given 1 byte null override associated the string, you can mess up with everything here. This 1 byte means the previous use and use of myself, with next objects, will be all wiped out. Meaning that whenever you do consolidations, in fact, you can lead into this benign null byte override into arbitrary read and write. Right? Because of these subtle implementations of heap metadata. Because one simple override ended up messing up with this state bit. So these are the exploitation technique that we're going to discuss next week. But here, the technique here is that we're going to utilize the free memory regions. So that we're still going to allocate just one additional word, but we can still maintain this one so that looking up the state of the free objects, previous object is free or not with the constant lookup operation. Right? Everything is constant in current implementation. What about free list? In fact, you don't need additional store for the free list even. So the typical technique that all the heap allocator is using so instead of maintaining a free list separately, in fact we're gonna keep track of the free list. Because this object is free, no one is using the contents inside. As a heap allocator, we're going to utilize them. We're going to keep track of doubly linked list in order to implement this nice tree in the sorting manner, so that unlink and append operation will be constant, right, after you look up the locations. So you're going to have the forward and backward locations, so that the forward point to the another object, and backward point to the another one, right? So that we have a doubly linked list that completely utilize on user space in the heap space, so that we don't need additional allocations as part of the heap allocator. Think about it. It's weird that heap allocator require the allocations of additional memory, right? It's a recursive problem. So in other words, by leveraging the free memory region, which a free list only required for the free object, we ended up having the space. So this is a pretty interesting design decision they made, right? But said that, what if you read the free pointer? Likely one of those values, which contain the data pointer to the next objects, so that you ended up breaking the entire layout of the heap allocations. But still, we have to do the O log n operation lookup for the free object that we like to find the proper free objects in terms of malloc. Is there any way we can improve this situation? How to make it constant? So there is a special data structure called bin. So the idea is pretty simple. Instead of having just one free list, we like to maintain multiple ones based on each size. Say we're gonna construct a binning structure. The first bin contain the object smaller than 32. For the second bin, we're gonna make sure that any object between 32 and 64 stay here. Similarly, we're gonna construct all the way down to, say, some page size, right? In this case, say you got the request of 50. What are you gonna do? You're gonna pick the closest one, 64, and do we have to iterate this free list? Oh no. If we are requesting if we are requesting 50, we have to iterate this guy so that we can pop. Basically, you can construct this way, the other way. So object here is all the bigger than 32, less than 64, in this case bigger than 64, and less than 128, etc. If you have a 50 requested, we're gonna pick this one, closest bin. You don't have to iterate this entire free list and pop the very first element in the free list, right? So you pop the very first one and just return. In most of the cases, you just feed one of those categories and return, right? What if we couldn't find anyone? It's just empty. What if it's empty? Exactly. We're gonna go to the next one. Up to this size, right? It's bounded. It means it's constant. Whenever you request a malloc, the lookup operation of the free objects now become constant, right? It's pretty nice. If system try to allocate bigger than certain page size, like 16 megabyte for instance, instead of creating this weird heap metadata, it's better to just allocate but invoke the system call, because big enough that it's worth reclaiming back to the systems whenever necessary. So we instead of having these two flag, as you can see here, previously in use and use, in fact there is an additional meta state information called M, whether this one is M map or not, right? For the object is map, it actually return back to the operating system. It's big enough that we just store back. In order to avoid this sequence of lookup whenever we don't have any free list, in fact, there are many other, I would say, optimizations. In fact, modern implementation of heap allocation have a bitmap they show the status of these guys as one bit. So the simple bit arithmetic quickly tell which locations that you can look up and look up the next object, right? Not only that, not just having this binning structure, there's another structure called fast bin. So in this case, instead of having this, think about these cases, we actually don't need a doubly linked list because we only pop up the first one. So instead of having this two bidirectional link, we only gonna have one, so that we can avoid additional store and maintenance of these data structures. We also maintain this fast bin per CPU to avoid the contentions among thread. So we call caching structure. Or in modern implementation of ptmalloc, there's a tcache. That per thread, they have a own binning structure to maintain this list by themselves. I think these are typical implementations in modern heap allocator. As you can see here, now we have pretty good performance. In terms of malloc, everything is constant. In terms of free, it's also constant. In terms of fragmentations, we kind of address internal fragmentations in this way by splitting. In terms of external fragmentations, we try very aggressively merge consolidate two different free objects before and after. We try to make it larger, so that whenever you requested something, in these special situations, we can handle this external fragmentation as much as possible. Also, we don't have to keep iterating this free list. So with a single lookup, we're gonna return back in certain size. For bigger size, again, we're gonna keep track of this doubly linked list so that we have a sorted tree, so that we can quickly look up those objects by log n operations. And in order to maximize the performance of CPU and modern architecture, we have a per CPU cache, per core cache, that maximize the hit rate and avoid the contentions of maintaining this metadata. Otherwise, you have to lock and update this metadata with all the atomic operations, right? Otherwise, you cannot support this multi-threading application. But in order to maintain this structure per CPU, you can actually drastically improve the performance. These are the simple constructions of heap allocation, but in fact it contains the most of the property that you can see in the ptmalloc that you're going to explore today in our tutorial. And we're suggesting digest the tutorial as much as possible. It's very complicated if you're not familiar with this heap structure. It's I would say, the marble. It's a well-constructed piece of software that evolve over time. And people are super happy about these allocations right now. Although modern applications like web browsers still have very unique characteristics, they have a special implementations of a heap allocator beyond ptmalloc that we're using, like jmalloc and tmalloc and whatnot. These are very advanced implementation of malloc that leverage the modern architecture. Unlike what we see right now with complex metadata, many of the performance-oriented, I would say, heap allocator do not rely on this in-place metadata. They keep separately for the security reasons. Okay. Thank you, everyone. And again, highly recommend to explore this tutorial by yourself today. Thank you.